Welcome back to lecture series on DC machines and transformers. In last class, we were discussing about armature reaction. We can just recap those things that we discussed in the last class. Initially, we defined what is armature reaction. It is nothing but the effect of armature flux on main flux, and its effects can be classified as demagnetizing effect and cross-magnetizing effect. And then we discussed main flux and armature flux separately. Main flux is nothing but flux that passing from main pole to armature pole. Main pole flux that is produced by main pole, that is passing from north to south. And the line perpendicular to the main flux is known as, what was that? Geometrically neutral axis. Then we discussed what is the resultant flux. When both main flux and armature flux are coming simultaneously, we will get a resultant flux. The line perpendicular to the resultant flux line is known as magnetically neutral axis. And we obtain the direction of main flux, that is from origin towards the x-axis, where the direction of armature flux is identified as origin, starting from the origin, and it is passing towards negative y-axis. Okay, so we can draw it. Where this is the geometrical neutral axis, where we are generally placing the brush, because brush should be there in the neutral axis, otherwise spark may happen at the commutation period. Okay, so this is the position of brush ideally, but it is correct whenever there is only main pole is present. If the flux in the system is just main flux that is passing from this north to this south, if only main flux is present inside the system, GNA and MNA are aligned on the same point. But if we are considering armature flux also, then resultant flux comes into picture, and MNA will be shifted according to the new resultant flux. So initially we are placing brush here, but we should be able to think that brush will not be placed here. Why? Because when armature flux appearing, we will get a new resultant flux, and then we have to shift brush to the new MNA, magnetically neutral axis. Otherwise, the brushes are situated on a magnetic area. This will cause spark. You have to write that. So, for finding that, we know that what was the case 1? Main flux was passing in this direction, phi m. And what was the second subheading? It was armature flux phi A. So how I can find the resultant flux? We can construct a parallelogram to find the resultant of phi m and phi A. This is phi r. So this is the resultant flux. So that where will be the new MNA? Magnetical neutral axis should be always perpendicular to the resultant flux. So you have to draw a perpendicular line. I hope this is perpendicular. This is our new MNA. New MNA. Why it is new? Because as per case 1, please go back to the previous video if you are having doubts. As per case 1, we are considering only main pole. So only main flux is present, so that GNA and MNA are aligned together. But now we are having a new resultant flux, so that MNA will shift, but GNA will be there in its original position, because GNA depends only on main flux. See this, GNA is perpendicular to main flux and MNA is perpendicular to resultant flux. So where I have to place the brush. That is my question. Where I have to place the brush. Okay, anyhow, we will think about it. I am going to draw the new MNA by measuring the theta degree. Okay, approximately I am drawing here. This may be the theta. I am extending it to back. This will be the new MNA. Okay. Now, we know that initially we were considering 5 conductors. This is the easy way to draw 5 conductors on each half circle. Okay. And what was the current directions? What was the current directions? Under North Pole, it was cross in all, whereas under South Pole, it was dot. Is it clear? So, what is the new change that happened to this figure? By checking this figure, in your notebook, you have to draw this one initially. Then you have to go to this figure. So, we got a new MNA and I reconstructed the new MNA by measuring the theta angle in the original figure. This is the third subheading. Resultant flux. Resultant flux phi r. Okay, this is the third case. So, you determine how much shift happened for the MNA to its new position. That angle is theta. That angle is theta. And you have to be very careful that if you are rotating in this direction machine, then theta should be happening in this side. You can check that if you are rotating the machine in the other side, then dot cross will change, everything will change. In that case, theta should be shifting towards that direction. You don't mind if you don't want to go up to that level. This is you have to think only this, but you have to keep in mind everything depends on the rotation of direction of machine. Okay. So, what is my next duty? Am I happy with this position of brushes? Now I know that this is not neutral axis. Is this neutral axis? It is just geometrical neutral axis. Magnetically it is not neutral. This is the new neutral axis. Can I just sit like this and let the brush sit there? Will my machine work in a fine tuning? No, because the brushes are used to collect the current towards outside and to give it back to the conductor. So, we are collecting the current from this point. If it is not a neutral point, what happens? Spark will come to the picture. For avoiding that, I have to shift the brush to the new position. I have to shift the brushes to the new position. Then what happens? If I am shifting this brush to this position, what happened to this conductor? Will it be again, can the conductor carry the same current just as before? No, because just after brush, the current reverses its direction. That is the concept. Just after the brush, because here we are going cross and this current is taken outside and this is another cycle. We will get a clear picture of this concept of reversing at the brush axis while discussing commutation. We will go to that. For the time being, you have to keep in mind that after the brush axis, current direction changes. So if I am placing the brush into new position, then what happened to this conductor? This conductor will take a cross current. Similarly, at this position, if I am taking brush to this axis, then this conductor, after that, this conductor will carry a dot current, because up to the brush it will be dot, after the brush it will be cross. So that I am going to represent in the next figure. Okay, is it clear? Let us move to the next slide. Okay, so this is the fourth subheading, where here I am finding the new direction of armature flux. Why? Because in this case we are shifting the brush to the new position of GNA. We know that the GNA is shifted by theta degree. Theta, both are same. So initially brush MNA was here, but now the MNA shifted to new position. So brush also shifted to new position in order to achieve sparkless commutation. You please write the word, in order to achieve sparkless commutation. We have to avoid the sparks in the brush. Okay. So in the new position, what happened? This conductor was initially dot, but after shifting the brush it will become cross. And this was initially cross, but after shifting the brush it become dot. Okay. So this is the new position of armature winding currents, new alignment. The armature windings current distribution is alignment is changed to the new case. So again we have to check the direction of armature flux, just same as the case 2, but the position is different, brush position is different, conductor's alignment is different, but the procedure is same. How we how we determine the armature flux direction in case 2? We applied Fleming's thumb rule, right hand thumb rule. Okay, so this is cross. Okay, I will take another color. So this is cross, means cross. This is the direction of flux. In all these conductor, this will be the direction of flux. So what happened? If I am grouping the 5 conductors together, I will get a flux direction like this. This is the resultant loop, flux loop, and the direction will be also inclined with respect to the new axis. So this will be the direction clockwise. And in these conductors, as these are carrying a current towards outside, the thumb should be placed towards me. So current will be like this. In all the conductors, it will be like this. Which is the direction, clockwise or anti-clockwise? It is anti-clockwise. Now I am grouping these 5 conductors together, so that I will get a flux distribution shape like this, and the arrow mark will be in anti-clockwise direction. Now, what will be the single flux line? What will be the resultant flux line? How I can draw? I have to draw a straight line from top to bottom with the same inclination of new MNA. So this will be phi A, new armature flux. It is also inclined by theta degree. Actually, you have to draw it in the center. It should pass through the origin. For simplicity, I have shifted a small space in order to get clear visibility. So this is the net flux. That is, if this is the coordinate system and this is the new MNA axis, what you can see is armature flux, new armature flux is also aligned at the same line. So, in the coordinate system, you can represent it with a line starting from origin with the inclination of theta with negative y-axis. This is the phi A. This is the net armature flux that is acting inside the machine after armature reaction. Okay. Now, what is the significance of this axis? Initially, we know that this was the direction of main flux, phi m. This was the direction of main flux. And this is the new direction of phi A that we obtained in the step 4. Now, I want to split the phi A into x-axis and y-axis. I know everybody know this step, resolving into components. You will get an x component and a y component. So, what will be the name of these components? This is the x component, sorry, this is the y component and this is the x component, and this is the theta. So, can anybody calculate the value of the y component? Y component of phi A is equal to, negative is not needed, phi A cos theta. And what is the x-axis component? X component of phi A, that is equal to phi A both. If you need, you can mark negatives also. Phi A sin theta, this component. So, this is phi A cos theta and this is phi A sin theta. Now, tell me which is demagnetizing component and which is cross magnetizing component. This is the conclusion. In the first area, in the previous lecture, I told you that there is two effects, demagnetizing effect and cross magnetizing effect. Cross magnetizing effect. Okay, you can write it as component. Cross magnetizing component. You got two component. The magnitude is specific, you don't need to put the negative. If you put it, then also it's right, nothing wrong, but the magnitude is just enough. So, which component is demagnetizing? This one or this one? Demagnetizing the main flux. Demagnetizing the main flux. From the figure itself it is clear. This component just opposite to main flux. So, it will demagnetize. So, that is phi A sin theta. And what is the cross magnetizing component? This is the main flux and this component is acting from top to bottom. Like this is the main flux and some component is acting like top to bottom. This is the main flux. So, this component is demagnetizing or sorry, this component is cross magnetizing or distorting the shape. So, its value is phi A cos theta. So, everything is covered in this title. We obtained in this class, what we did is we obtained the new MNA direction, then we shifted brush to the new direction, then the conductor's current direction alignment get changed. Now we determined the phi A from the new alignment in case 4. That phi A was in a shift of theta degree with the y-axis, and we shifted that phi A into x-axis and y-axis, and we obtained that the x component is just opposite to main flux. So, it is demagnetizing component, and Y component is acting in cross with the main flux, so it is cross magnetic component. So phi A sin theta and phi A cos theta, demagnetizing component of armature reaction and cross magnetizing component of armature reaction. So hope everybody enjoyed this video. We'll meet in the next class. Thank you.